Oscillate means to go back and forth. Is that right? Yes. I have an example of an oscillation here. Now, this is a loaded spring. If you look at the spring, a mass is suspended from there. The position of the spring, the mass now, this position is called its equilibrium position. Now, if I pull it down from the equilibrium position, if I pull it down, what happens? I would want you to watch what happens. I'm stretching the spring. When I stretch a spring, you know, I supply that with potential energy. So, the spring is stretched, it has potential energy. So what happens when I leave this mass? Because of the potential energy, the spring will do work. There you are. Setting the mass into oscillation. Now, if you look through the energy changes, we will be looking at this as we go on. The stretched spring has potential energy, and that potential energy gets converted to kinetic energy of the mass. The kinetic energy will compress the spring. You see how the spring gets compressed? The compressed spring has potential energy, and that potential energy will then push the mass back, giving its kinetic energy. You can see energy gets converted from potential to kinetic and back at a continuous rate. And this is an example of oscillation. All right, let's talk more about oscillations. If a loaded spring is pulled down and released, the system moves up and down. I have an illustration here. The same thing I just showed you. The system moves up and down about its equilibrium position. You understand what that equilibrium position is? Well, the equilibrium position is over here. It goes to a lower extreme, comes back to the equilibrium position, then goes to an upper extreme, and the oscillation is between a lower extreme and an upper extreme. This up and down motion of the load is called an oscillation. So an oscillation is, this is a good example of an oscillation, the up and down motion of the load attached to a spring. When the load is pulled down to the lower extreme, this is the lower extreme, the work done in stretching the spring becomes potential energy of the spring, which then pulls the load back, giving its kinetic energy. That means the load will now rush back to the equilibrium position. Alright? And now, when it gets back to the equilibrium position, can the load stop there? No, it cannot. Why not? Because it has now acquired a speed. You see, by rushing back because of the potential energy of the spring, it has acquired a certain velocity at the equilibrium position. Therefore, it cannot stop there. It will move up, compressing the spring. The kinetic energy at the equilibrium position does work in compressing the spring so that the load moves to the upper extreme. That is the upper extreme. Now, the compressed spring now has potential energy, and it does work pushing the load back to its equilibrium position. Now, that means the load now rushes back to the equilibrium position from here. But when it comes back to the equilibrium position, can it stop there? No. Why not? Because it has now a speed, and its speed takes it to the lower extreme, and when it does so, it will stretch the spring, giving the spring potential energy. Now, you can see how the exchanges of energy take place. The spring has potential energy when the load is at either extreme. So the spring has maximum potential energy when the load is at the lower extreme and when the load is at the upper extreme. Now, in between, it has both potential energy and kinetic energy. Alright, at the equilibrium position, the potential energy of the spring is 0. Do you understand that? Well, at the equilibrium position, if you notice here, the load is now at the equilibrium position. Now the spring is at its natural length. The potential energy is 0. The potential energy is maximum when the load is at the lower extreme, and also when it is at the upper extreme, when the spring is compressed to its maximum. So the load has maximum, the spring has maximum potential energy when the load is at either extreme. And how about the energy of this mass? When will this mass have the maximum velocity? Its velocity is 0 at the lower extreme. Its velocity will be 0 at the upper extreme. Now, from the upper extreme it gets pushed down. So when will the velocity become maximum? At the equilibrium position. So the load has maximum kinetic energy because its speed, it has kinetic energy at the equilibrium position. So I hope you are able to trace the energy changes that take place during the oscillation. So let's look at the equilibrium position. At the equilibrium position, the potential energy of the spring is 0. The kinetic energy of the mass is a maximum. I hope you can read this. Potential energy is represented by U. I hope you know that. We discussed all that in Physics 1. K stands for kinetic energy. At the equilibrium position, the kinetic energy is maximum and the potential energy is 0. At the upper extreme, the kinetic energy is 0. The load is momentarily at rest at the upper extreme and the potential energy is maximum. The spring is compressed to the maximum level there. Similarly, at the lower extreme, the potential energy is maximum because the spring is stretched to the maximum and the load is momentarily at rest there. Its kinetic energy is 0. The amount of stretch of the spring from its equilibrium position is called the displacement Y of the load. You can see the load is at the equilibrium position. As it keeps moving up, the displacement Y, you can see at any particular position, the distance the load moves from the equilibrium position is called the displacement, and we will represent that by the letter Y. Now, can you look at this and tell me what is the maximum displacement of the load? The maximum displacement occurs when it is at the upper extreme. That means the displacement at that time will be this displacement where I have used the white braces. Now, this displacement is called the amplitude, represented by A. So what does the amplitude mean? Amplitude of oscillation is the maximum displacement of the oscillating object, and displacement is measured from where? From the equilibrium position. That means the displacement can be positive or negative. An upward displacement is positive and a downward displacement is negative. Alright? As the load oscillates between the two extremes, from lower extreme to upper extreme and back, the displacement Y changes. Can you trace out and tell me how the displacement changes. Well, watch this carefully. At the equilibrium position, the displacement is 0. As the load moves up, the displacement increases, reaches the maximum. And what is the displacement when the load is at the upper extreme? It is the amplitude, the maximum displacement. And then the displacement begins to decrease, reaches 0, and now it is going to go down. The displacement now is negative. It goes to a negative minimum and then increases to 0 and then increases to a maximum, and that is how the displacement y changes with time. It's very important to know how that displacement y changes with time. Okay, so the displacement changes from maximum value a to minimum value negative a, and it increases to a maximum, decreases to 0, and decreases to a minimum, increases to 0, and so on. We will now obtain an equation for the displacement y as a function of time. Well, and that is the most important part of this discussion. We now need to represent the equation, or an equation for the displacement, in other words, as the load oscillates between an upper and a lower extreme. You can see here, this is the equilibrium position. The displacement increases to a maximum, decreases to 0, decreases to a minimum, increases to 0, and so on. We will now obtain a mathematical equation for the displacement as a function of time. Alright, let's do that. Now, before I do that, I would like to show you a couple of examples of oscillations. Now, look at the same example here. The loaded spring is oscillating up and down, and look at how y changes. Y is 0 here. This is the equilibrium position. Y increases to a maximum, decreases to 0, decreases to a negative minimum, back to 0, and so on. And we are going to obtain a mathematical equation for the change in this y as a function of time. Now look at another type of oscillation. Now this type of oscillation is called a torsional oscillation. A torsional oscillation. And the displacement here is angular displacement. If you remember, we talked about rotational motion in Physics 1. So torsion is actually rotation, and the displacement is angle theta. And angle theta is 0 at the equilibrium position. Theta increases to a maximum and then decreases to 0, decreases to a minimum, and then increases the same way as y changes. So y for this kind of oscillation and theta for torsional oscillation follow the same kind of change. Alright, let's go and look at another example. Let's look at this.